Okay, so we discussed electric charge, electric forces. We learned Coulomb's law. We used Coulomb's law to calculate the force on a single charge if it's in a group of multiple charges, right? The rule is that you just repeat Coulomb's law for each pair. You just pair it up with every other charge in this combination. You just repeat using Coulomb's law to find the magnitude and direction, and then you're gonna and remember they're vectors, right? You're gonna break all the vectors into x and y components, add x components together, add y components together. Now at the end, you use the x component of the net force, y component of the net force, combine them to get the net force, the magnitude, and direction, right? So in principle, you can generalize that, right, to 100 or 1,000 charges, right? But at the end of the last lecture, as I said, physicists always want to do things, try to find an easier way to do the calculations, okay? So in this case, by introducing this new concept, the electric field, you can make the calculations of the electric force a little bit easier, okay, once you find the electric field. Okay, so finding the electric field is still hard. It's still going to involve a lot of work. Okay, you can't avoid that work. But once you have found the electric field, finding the force, it's going to be a lot easier. Okay, so that's what we're going to do this time. Electric field is a very abstract concept. If this is the first time you see this concept, it's definitely going to take you a lot of time to digest it, to get used to it. Okay, it's invisible. Okay, you can see that. Okay, that's why it's hard for people to visualize it, to study that, to accept this concept. Okay, why do we need this concept? First of all, as I think about it, when there's a charge like Q1 and Q2, then from Coulomb's law, there's a force between them, right? Q1 has a force on Q2, repulsive, and Q2 has a force on Q1, repulsive. And then the weird thing is this: they don't need to be in contact, okay? They don't need to be touching each other to have this force between them, right? And if these two charges are very strong, even if they're like meters apart, they still feel forces from each other. And this is really weird if you think about it, right? What is really going on between these two charges? There must be something between them to transmit the force, right? To exchange the information between them. How come Q2 knows there's a charge there, Q1, called Q1, and then it has a force on me? They're not even in contact. And then say there's like 1,000 charges around Q2. Every single charge, Q2 is going to feel a force from them. And that's really weird, right? If there's nothing between them, how can this nothing transmit the force, right? What is carrying this force, okay? You can also think about gravity, because the gravity is it's similar to this, right? Think about the gravity between the Earth and you, right? Do you need to be in contact with the Earth in order to feel the force? You don't. Well, I do stand on the ground every day, right? But even if I'm not on the ground, I can still feel the gravitational force from the Earth on me, right? Say if you're flying on an airplane, you're not in contact with the Earth directly. You still feel the force. The force doesn't disappear, right? What is really going on between you and the Earth, right? So you think about it, there must be something between them, okay, to transmit the force. There must be some agent, okay? Or think about the Earth and the Sun, okay? You can Google up the distance between them, okay? It's about 100 million miles. It's about 100 million miles between the Sun and the Earth, and there's literally nothing between them, not even atmosphere, right? Not even air between them. How come the Earth can still feel the force from the Sun? And we know that it does feel the force from the Sun, because that's why orbits the sun, right? And every planet, okay, pretty much everything in the solar system can feel the gravitational force from the sun, okay? And if you think about it, right, you can explain that what is really going on between the sun and the earth that transmit the force from the sun to the earth over 100 million miles, okay? So that's why physicists need to introduce a concept called field, okay? So physicists realized what is going on between the earth and the sun, or between these two charges, is there is a field. There's a field between them, and this field is created, the field is created from the sun. It's called gravitational field, okay? When the earth is in the gravitational field created by the sun, it feels a gravitational force. That's the consequence of the earth sitting in the gravitational field created by the earth. Q1, this charge creates its own electric field all around it, okay? All around. Of course, it's going to get weaker and weaker when it's far away from this charge, but it creates electric field all around it, okay? And if it's not strong enough, right, so when you're like far enough from it, you don't feel this, becomes very weak, okay? But it creates electric field all around. Q2 sitting in that electric field, it's going to feel a force. Q2 doesn't even know Q1 exists, right? Q2 only feels, I'm sitting in like the electric field. What is the consequence? I feel a force. Everyone, sit in the gravitational force created by the earth. I don't even need to know it was created by the earth, right? Before Newton, no one knew that, okay, the weight we feel every day is actually a force between myself and the earth. But as long as I'm in the gravitational field created by the earth, I can feel that, right? I don't even need to be in contact with the earth itself. As long as I'm in the field created by the earth, I feel the field, I feel the force. That's the consequence, right? The earth is in the gravitational field created by the sun. That's why the earth feels a gravitational force from the sun. So there is something between the sun and the earth. That's the gravitational field created by the sun. Invisible, okay, we can see that, but it exists. How do I know it exists? Because there is an effect on the earth, right? If there's nothing between them, there shouldn't be any effect from the sun on the earth, right? There is a gravitational force on the earth. And how come there's a gravitational force on the earth? Because it's in the gravitational field created by the sun, okay? It's invisible to us, so that's why you will feel it's very abstract, it's very difficult concept. Maybe to some aliens living in a different planet, they see fields. They won't say that field is a very weird, very abstract concept to them, right? Because they can see that, okay? Remember what we can see, the visible light we see, actually we're going to discuss that at the end of this class. It's only a very small, very narrow spectrum in the E&M, a very narrow region in the E&M wave spectrum. There are a lot of things we don't see. X-rays, gamma rays, microwave. Do they exist? Do microwaves exist? Of course they exist. You use them every day, right? You can see them, right? But they do exist. They're also electric E&M waves. They are E&M waves created by E&M fields. We're going to study that at the end. Okay, so see that we do use them, we make use of them. They do exist, okay? It's just we don't see them. So the first time you learn this concept, you're gonna feel a little bit weird, okay? So the first time I learned this concept, electric field, it did take me a lot of time to really accept this concept, okay? Now it's like as real as a chair to me, okay? It is real, I know it exists, but it takes time, okay? So it's going to take you some time to get used to this concept, to accept this concept, to get familiar with that, okay, the best way to do that is to practice. Practice a lot. You will get used to this new concept, okay? And think about this. We know that dogs, they have a better range of hearing than us, right? They can hear more sounds than us, right? So to us, some sounds don't exist because we don't hear them, but they exist to the dogs, right? So you can't say that, okay, these sounds, they don't exist because I, as a person, can hear that, so they don't exist, right? There are a lot of things we don't see, we can't sense, but they do exist, okay? If you only trust your senses, okay, the things you can understand are going to be very limited, okay? What science does is to help us go beyond, way beyond our senses. That's what science does, okay? So we use theories, we use models, we do math, okay? That's going to help us go way beyond our senses, okay? You shouldn't always trust your senses when you do science, okay? Then you're going to be very limited, okay? All right? So that's why we need this concept. You have to explain what is transmitting gravity, what is transmitting electric force, and also what is transmitting magnetic force, okay, as we're going to see later, okay. There is a field, okay, and then we do have evidence for this field. All these E&M waves, microwaves used every day, that's created by E&M field, okay. We're going to study that later, okay. So they do exist. Electric field, magnetic field do exist, but just to many people, it's really hard for them to understand this invisible concept, okay? So that's what we're going to do in this lecture, okay? Now, as I said, now we're going to view the interactions between these two charges in a different way, okay? We don't say that, okay, there is a ghostly force from Q1 and Q2, which requires nothing between them to transmit, okay? As long as Q1 is here, Q2 is here, some magic happens, then there's a force between them. No. Q1 creates the electric field. Q2 feels that electric field. Consequence, Q2 feels the force. Right? Q2 also creates its own magnetic field, or electric field. Q1 is in that electric field. That's why Q1 also feels the force from Q2. So there is an electric field between them. That's the carrier of the force. Okay, that's what transmits the force between them. Okay, all right. So that's conceptual. Okay, that answers the question: what is really going on between these two charges to transmit the force? Okay, then what is the formal definition? The definition is this. So if there is an electric field created by something, okay, it's created by source, we call it source, like this big Q, we call it big Q. This big Q creates electric field all around it. You can't see that, but it exists, okay? You should never only trust your senses, okay, when you do science. How do I find the electric field how do I define the electric field at this point? You can't see that, you don't see that, okay? But it exists, okay? That's why we use math to study that, because we don't see that, okay? How do I define the electric field at this point? I would bring a test charge to help me do that. I would bring a very small charge, like positive Q0. And then if there's an electric field in this region, Q0 is going to definitely feel a force, right? Q0 doesn't even know what created this electric field. And he doesn't need to know that, okay? He just feels the electric force, say, oh, in this way. Okay, then Q2 confirms there is an electric field in this region, because I can feel that force. What is the definition of the electric field, okay? The definition all the physicists agreed on is this. You bring this Q0 here, you can measure this force, if you can. You divide the force by this Q0. That's our definition of electric field. So that's a definition. As I said, you can define anything any way you like in physics. The only matter is that if you can make a complete and consistent and useful theory out of your definitions, right? Velocity, what is velocity? Distance over time, right? Why do we define it that way? Because it's useful. I can use that to describe how fast something's traveling. I don't need to use words because I'm going to run out of words very soon, right? Fast, slow, very fast, very slow, right? But if I define that, I calculate a number, I can compare, you know, the velocity of different things. Okay, I can make predictions, I can explain things, okay? And then, so that's why, okay, everyone agreed, let's define something called velocity, always distance over time. And that's the best definition to describe how fast something's moving. So everyone in this world agrees on that. So every time we talk about velocity, we know what we're talking about. This is the definition all physicists agreed on, okay? This is the best definition. We can make a complete, consistent, and useful theory out of it, okay? Maybe in a different planet, these aliens, they will define field in a different way. But as long as they can make a complete, consistent, useful theory out of all these definitions they defined, good, that's also a good theory, okay? So this is the definition all the physicists on the Earth, okay, agreed on. Let's define electric field this way, okay? Don't argue with that because we're going to make a complete, consistent, useful theory out of this definition. That's the point. Okay. If you define it that way, the unit is going to be newtons per coulomb, right? Because this force is in newtons, charges in coulombs. So we're just going to call it newtons per coulomb. We're not going to give it a new name, okay? And then remember, this guy is a vector because force is vector, right? If you divide a force by a number, the charge is a number. But remember, the charge can be also positive or negative, right? This is the vector equation, so everything can be. I didn't use any absolute value sign, okay? So the electric field is also going to be a vector. So electric field is going to have a magnitude and direction, okay? It's a vector, okay? It does exist. We don't see that it exists. Okay. Now, what's the use of this definition? Okay, why did you say that it's going to make our calculations of electric force easier than using coulombs? So I'm more familiar with coulombs, so why do I need to switch to this? Okay. If you rearrange this equation, you would get this, right? And that's very easy. If you rearrange this equation, you can find that the electric force on a test charge is going to be the test charge times the electric field at that point, right? So that means if you have the electric field at that point, okay, and then I want you to find the force on this Q naught, okay, you just multiply them together. Isn't that easy, right? But that's because we assume that this electric field can be calculated in the first place, okay? So how do you calculate electric field? We're going to find a theory, okay? So this may sound a little bit circular to you, right? Is this a circular argument? You told me that electric field is how do you define electric field? You're going to use the force divided by the charge, okay? So you need to find the force. You need to bring a test charge. And then you tell me that, how do you use this definition? Well, you find the electric field force there, and then you can find the force. So this is sort of a circular to me. Now, this is not, because we will find a fundamental theory. So even though this is a definition of E, electric field, we will find a fundamental theory to calculate the electric field. So every time we want to find the electric field, we're not going to use this definition. We're going to use that fundamental theory to do that. So we will have a fundamental theory to calculate the electric field. Okay, which is not that easy. You can't avoid that work. That's still hard, okay? But once you find the electric field using that fundamental theory, okay, say I already calculate at this point, the electric field is in this way, 5 newtons per coulomb. I've done the hard work. I've spent like 4 hours doing that work. I calculate this is 5 newtons per coulomb. Then, if you tell me you bring a charge 2 coulombs at this point, okay, what is the force this 2 coulomb charge feels? Okay, easy. The force it feels is going to be 10 newtons. How do you get that? Multiply these two numbers. You see that? right? So that's what I meant. If you can calculate the electric field in the first place, okay, which is going to be hard, and that's what we're going to do next, okay. Once you have done that, once you have done the hard work, this step, finding the force, it's going to be very easy, okay, because you just multiply the charge and the electric field, okay. So that's what I meant by introducing the electric field. Calculating the force will be easy, much easier than using Coulomb's law, right? Imagine this electric field is created by 1,000 charges, right? If you want to use Coulomb's law, you're gonna break 1,000 vectors, right? And then components, and then combine the components, and then you do trig again to find the net force. But if you can find the electric field 5 newtons per coulomb, or someone did that for you, and you want to find the force when you bring a 2 coulomb charge, multiply them together, right? What if I bring a 3 coulomb charge here? Okay, multiply them together, 15 newtons. What if I bring a 8 coulomb charge here? Multiply them together, 40 newtons. Easy, okay? So once you have found the electric field, which is not easy, okay, you can avoid that work, okay? We're gonna do that. That's what we're gonna focus on, okay, next. Once you have done that hard work, finding the electric force, it's gonna be very easy, okay? So that's how we use this definition to help us calculate the electric force easily, okay? But you should be careful. When I ask you the force, okay, it has magnitude and direction, right? How do I find out the direction, okay? That's also this equation. So now you should be careful. Whenever you use so I'm assuming that we have already found the electric field, okay? Now I'm just calculating the force. So there's the electric field at this point, 5 newtons per coulomb in that direction. I have done the hard work. Okay, you don't need to worry about it. I'm just going to tell you, I did the hard work at 5 newtons per coulomb in that direction. I can bring different test charges here, right? 5 coulombs, 2 coulombs, 3 coulombs, 100 coulombs. I want you to calculate the force. Okay, you would say easy. The magnitude of the force, it's just going to be the magnitude of these two numbers multiplied together. That's what we just did, right? You bring a 2 coulomb charge, multiply 2 by 5. 100 coulomb charge, multiply 100 by 5. Easy. But the force also has a direction. How do you find the direction? You also make use of this theory, okay? The theory tells you the force is going to be the charge times a vector E, right? And this charge can be positive or negative. So think about it. If you multiply a vector by a positive number, you're just changing its magnitude, right? If you multiply a vector by 2, you're just doubling its magnitude, right? Initially you have this vector, now you're going to have twice long, okay? So if this is a 2 coulomb charge, I bring here, the force on it is going to be 10 newtons, and the direction is just going to be in the same direction, right? So I would draw it this way. Okay? So that's how we use this theory to find the force once the electric field has already been calculated. So if you bring a 3 coulomb charge, okay, 15 newtons in the same direction. Because when you multiply a vector by a positive number, it's not going to change its direction. It's just going to change its length, right? If you bring a 0.2 coulomb charge, the force is going to be 1 newton, okay? So it's going to be shorter, but the direction is still going to be in the same direction, okay? So that's the rule for the direction if the test charge you bring in is positive, right? What if the test charge you bring in is negative, right? So I'm going to still use that. Okay, I've done some calculation. There's an electric field in this direction, 5 newtons per coulomb in that direction. The same electric field, the same point. What if I bring a charge? Now I'm going to put a charge, negative 3 coulombs here. What is the force on it? Okay, you would tell me, okay, force 15 newtons. What is the direction? Now, if you multiply a vector by a negative number, it's going to change the magnitude, but at the same time, it's also going to change its length, the direction, okay? So in this case, if you multiply a vector by a negative number, I hope it's intuitive, right? Intuitive, it's just going to reverse the direction, right? So the force is going to be 15 newtons in the opposite direction, okay? So that's how you use this E to find the force on a test charge, okay, at this point. Very easy, okay? Magnitude, you multiply these two numbers together, make everything positive. Direction, you take a look at the sign of this test charge, okay? If the sign of the test charge is positive, the force is going to be in the same direction as the field. If the charge is negative, the force is going to be opposite to the field. Okay? So that's the rules for the direction. Magnitude, easy, multiply them. Okay? That's what I said. It's going to make the calculations of force easier. But still, you have to find this E first, right? Finding this electric field is going to be hard. So let's compare this to gravitational field. So you're going to see what I meant. Okay? Why calculating this electric field is hard, and then why, after these calculations of the field, calculating the force is going to be easy. Remember, what is the gravity equation we use to calculate the gravity of anything on the Earth? M times little g. What is little g? 9.8, right? 9.8 meters per second square. So that means when I ask you, I have a 5 kilogram object. What is the gravity on this guy? You would say, okay, 5 times 9.8. Do that. That's going to be the force on it. Okay, I would ask you another question. What about it's a 10 kilogram object? You would say the same thing. 10 times 9.8. Right? Then I would ask you, what about it's a 15 kilogram object? You would say, hey. Okay, if you keep asking me, I'm just going to tell you one thing. All you need to do, whatever the mass is, multiply that by 9.8. That's it. Don't ask me another, question with a different mass. You know the rule. Multiply the mass by 9.8. You get the force. That's it. Okay. You can ask me a different type of question, but this type of question, we're done. Okay. That's similar to this. Right? Once I have calculated the E at a specific point, I put different test charges there. All you need to do is just multiply the test charge by this magnetic electric field. That's it. Okay? So you see that calculating this force, the gravitational force, or calculating the electric force this way, it's going to be very easy, right? So this Q naught is like the mass that can change, right? You can ask me about a 5 kilogram object, 10 kilogram object, 15 kilogram object. That's fine. You will get different numbers, but this field, it's going to be the same, right? If it's the same point, okay? So if it's on the surface of the Earth, it's always 9.8, okay? It's always 9.8, okay? Then I would ask you, how do you know it's 9.8? Right? How did you get this 9.8? Well, okay, you would tell me, if you still remember that, well, this 9.8 actually comes from a fundamental theory which was discovered by Newton, which is this theory. This is what we learn in physics 1. So for any two objects, there is a gravitational force always attractive between them, right? How do you calculate that force? Big G times the product of these two masses divided by the distance squared. Okay? And then you would say, then you would apply that between the Earth and any object on the surface of Earth. What do you get? You would get this. And we did that in physics 1, if you still remember that. So the first mass is going to be the mass of the Earth. Right? The second mass is going to be the mass of the object. So whatever object you give me. Now the radius, the distance now is going to become the radius of the Earth. If you just want to find a force for any object on the surface of the Earth, right? Okay? And then you would say, okay, now the magic is this. Now let's factor out this little m. So this is going to change, right? Of course, you give me a different object, m is going to change. Now let's put all the other guys together. Okay? And these three guys, take a look at them. They're going to be constant. They're not going to change. Big G, constant. The mass of the Earth, no, it's not going to change. The radius of the Earth, no, it's not going to change. Okay? So you put these three numbers, they're not going to change. Every time you want to calculate the force of gravity of anything on the surface of the Earth, this number changed. These three numbers don't change. Okay? So all we need to do is actually calculate this factor once. Okay? Then just use this factor for all kinds of objects, right? So we did that in physics 1. If you took physics 1 with me, or okay, if your professor did that with you, you put the mass of the Earth, the radius of the Earth, and the big G, the constant, you will get 9.8 meters per second square. Okay? Then you would say, okay, now I'm telling you, where does this 9.8 come from? It's from a fundamental theory discovered by Newton. Okay? And then once you have done the math, you realize that you will get a shortcut equation, which is going to be the mass of the object, multiplied by a constant 9.8. And because this is always a constant, so we don't need to do this every time I want to calculate the weight of anything on the surface of Earth. I would just say, hey, why don't we call this guy a new constant, right? Let's just call this guy little g. Okay? So if I call this guy little g, and then boom, this shortcut equation, okay? So if you feel this is very complicated, that's fine. Go ahead and use this equation, right? If you want to calculate the weight, the force of gravity of anything on the Earth of the surface, on the surface of the Earth, mass times 9.8. That's it, right? I have already done hard work for you. I have already found the little g, which I would call gravitational field created by the Earth, right? So I have done the hard work. The little g is the gravitational field created by the Earth. So I've done the hard work for you, okay? Actually, Newton did that, okay? And then you just go ahead and do this, right? Isn't that easy, right? I've done the hard work. If you want to find the force, mass times the field, okay? It's the same deal in electric field. You still need to find it, that's what we're going to do. We still need to find a fundamental theory to help us calculate electric field for any distribution of charge, which is not going to be easy, right? Which is not going to be easy. And then once you have done that hard work, calculating the force for any test charge in that electric field, it's going to be easy. And then if it's arbitrary electric field, the number is going to be different everywhere, right? This 5 Newton per coulomb is going to be here. Maybe I pick a point here, it's going to become 6. A point here, 10. But again, if I have a fundamental theory, okay, then in principle, I can calculate the electric field created by any charge distribution at any point, right? So if I can do that hard work, calculating this electric field, electric force on an arbitrary test charge I bring into this electric field, it's going to be super easy as doing mass times 9.8. Of course, this is even easier because this 9.8 on the surface of the Earth doesn't change. But remember, we did this, we solved some problem. When you go to a very far distance above the Earth, this is going to change, right? So you still need to repeat this fundamental theory to calculate little g at that point, so you can calculate the weight of something like 700 kilometers above the surface of Earth, right? On the surface of Earth, this gravitational field is almost a constant, 9.8. That's why you can just do that. But if I pick a different point, very far away from the surface of Earth, you're going to calculate that. But don't worry, I still have the fundamental theory. So in principle, I can calculate the weight, the gravitational field at any point above, even above the surface of the Earth. And then if you want me to calculate the force of an object at that point, I would just do mass times the gravitational field at that point. Okay? So it's the same deal here. We still need to find the fundamental theory to calculate the electric field. But once we have done that, it's going to be very easy. Okay? All right? So that's the idea. That's why we wanted to introduce the electric field. Okay? Now, of course, we don't see electric field, right? So how do we work with them? Okay? So then physicists decided we can draw some lines to help us visualize this electric field. Think about forces. Do you see forces? You don't, right? So how do we work with forces in physics 1? We draw them out. We draw a free body diagram with all the forces represented by arrows, right? Like what we did last time, right? So we draw arrows, we draw lines to help us visualize vectors, okay? Excuse me. We're going to do the same thing here. We're going to do the same thing here. We're going to draw these lines, we call them electric field lines. Okay, we use them to help us visualize electric field. Okay, so of course we're gonna set some rules for these electric field lines. So that means all over the world, people all over the world, when they draw electric field lines, they should be able to understand each other. Okay, all right. So what are the rules? Take a look at the rules on slide 4. This is PowerPoint 2. So first of all, we can use the electric field lines. When we draw the electric field line, we can use the electric field lines to figure out the direction of the electric field at any point. Right? So the electric field lines, they don't have to be always straight. Right? They can be in any arbitrary shape. Right? So for example, if I have electric field lines in a region like this, okay, so at least I can find the direction of the electric field at any point, okay, by drawing the tangent to that point, right? For example, what is the electric field at this point? It's going to be in this direction. What is the direction of the electric field at this point? Tangent. What is the direction of the electric field at this point? Tangent. Okay, so the electric field, that's how we define the direction of the electric field. Okay. We can also use the density of the lines to help us visualize the strength of the electric field quantitatively. So we can't figure out the number, the value of the electric field based on these lines, but we can get an idea, okay, how strong they are. We can compare the strength of the electric field at different points based on these lines, okay? So our rules is this. If the lines are very close to each other, that indicates the electric field is very strong in that region. If the lines are far apart, then that means the electric field it's very weak in that region, right? So if I have, take a look at the image on this slide, right? If I have these lines going this way, okay, and in a region there's some electric field, and then I use these lines to represent the electric field. Okay, so even though you can't really see the value of the electric field at any point, but you can figure out this point A and this point B. At least I know that the strength of the electric field at point A is going to be stronger than point B, right? Because these lines are very close in this region. Okay, so I hope that's intuitive, right? And then another rule we set is that electric field lines, they never intersect. Okay, so this is a little bit special. So that means when we draw electric field lines, when we discuss drawing electric field line, we want to discuss electric field with another person. Okay, you can never draw something like this. Okay, if you draw this electric, you say that okay, I just calculate the electric field created by some charge, and then I got this. So I don't even need to check your work. I would say this is wrong. Okay, why? Because this is going to violate the rules we set at the beginning. Take a look at this point. Okay, where they cross each other. If I ask you what is the direction of the electric field at this point, you would say, oh, the rule is this. The direction of the electric field is going to be tangent to the line at that point. But now you have two lines crossing this point, right? So is the direction this tangent or is the direction this tangent? Okay? Okay, that doesn't make any sense because it must have a unique direction at this point, right? But if you draw these two electric field lines crossing each other, then you can determine which one is the actual direction of the electric field right at this point, right? So you can never draw that. You should never draw two electric field lines crossing each other, okay? And then the last rule, so this is totally conventional, right? And then electric field lines, we always draw them from, they start from positive charges, they end on negative charges, okay? So this is totally conventional, right? You can just say that I want to set the rule the other way around, like they start from negative charges, they end on positive charges. There's nothing wrong, okay? But this is the convention everyone agreed on, so we're going to use that convention, so there's no confusion when we talk about the electric field with a different person all over the world, okay? So drawing electric field lines is not that easy, okay? But for a point charge, for a single point charge, the electric field lines are very easy to draw. Take a look at the lines on slide 5. Like if you have a positive charge, single positive point charge, the electric field lines we draw are just going to be the lines radially outward, okay? Radially outward. So you're just going to draw lines coming out, okay? So these lines, they are outward. These are the field lines, okay? Field lines, okay? If there's a negative charge, okay, the other way around, right? So if it's a negative point charge, you want to draw the electric field lines to help you visualize the electric field. You're going to draw all the lines inward, okay, radially inward. But you should imagine that, be able to picture this in three-dimensional, okay? So if you have a point charge here, the lines are going like in any direction, not only on this plane, right? So you should also have field line this way and that way, okay? But all these lines are outward, radially, straight lines for a single point charge, right? A negative charge inward, okay, toward these charges, okay? But if you want to draw electric field lines for more than one charge, okay, that's going to be a little bit hard, okay? So you can take a look at these two images at the bottom, okay? That's the electric field lines when there are two charges present in the same region. But we're not going to really worry about that, okay? We're just going to still focus on, if I want to draw electric field lines, I would just draw electric field lines for single, positive, or negative point charge. Okay, so these are the electric field lines. We use them to help us visualize the electric field. Okay, so as I said, we still need to find fundamental theory to calculate the electric field for us. Okay, and that's what we're going to do next. We're going to start with Coulomb's law, and use Coulomb's law, we can find a fundamental theory to calculate the electric field for any charge distribution, okay? Using that fundamental theory, you can calculate the electric field, which is not that easy, but once you have done that, you bring a test charge to that field, calculating the force. It's going to be very easy, okay? So that's what we're going to do next time.